Hi, thanks very much for the introduction, and thanks for the invitation to speak from the organizers. So the title of the talk is Localized Representation Theory. It's joint work with Akshay Venkatesh, and it's I'll be talking today about a part of a project with the fancier title Period Bounds via Coadjoint Microlocalization. Okay, so I want to talk today about representations of a Lie group. And even this condition can be relaxed somewhat, but I'll be focusing mostly on the case of semi-simple ones. So we'll work with a unitary representation, which I'll denote by a symbol pi, and I'll employ the standard abusive notation writing pi both for the map defining the action as well as the Hilbert space where we realize the group as unitary operators. So there's a space one can attach to such a pi called the space of bounded linear operators. Which is by definition the space of linear maps with finite operator norm, which I'll denote by this. And then finally, given an element of the group and an operator, we can define an action that I'll denote by a superscript on the left given by conjugation. Okay, so with this notation, we can introduce a definition, or recall a definition. So A over there is called equivariant if, when we apply this operator G to A, we subtract off A, we get back 0. This is a standard definition of equivariance. Now there's a well-known result, a foundational result called Schur's lemma, which says that if pi is, moreover, an irreducible representation, and this assumption implies that each equivariant operator is a scalar, which means there exists some complex number, let's call it CA, such that if we look at the difference between AV and CAV for any vector in our representation, then this difference should be identically 0. Okay, this is a basic foundational result. It's a very useful result. It says, among other things, that if you have, for example, two equivariant or invariant inner products on a representation, perhaps defined by different models, maybe one model is easier to do a computation than the other, you can do the computation in your preferred model. So it's useful. There are at least two ways one can view this assertion. So what is the input? The input you can view as saying you have an equivariant operator. Equivariance is some sort of regularity condition on an operator. It says that it varies very slowly under the group action, as slowly as it can. It doesn't vary at all. And then this regularity is upgraded to some very precise classification of this operator. So it says it's actually exactly proportional to a scalar on the entire representation. So in one direction, you can view it as a classification of operators having some sort of regularity. In another direction, if you consider the special case where the operator is a projection operator onto a closed invariant subspace, you can take this as a definition of irreducibility. So these are two perspectives on a very standard result. What we'll do today is we'll introduce a superfluous quantifier into this statement. Call it exactly, which means exactly as it would if I didn't write that. So exactly means equal to 0. And then we'll notice that we can say the same thing here. It's exactly a scalar. We have this identity here. Something's equal to 0. And we'll ask what we can say and what are the ramifications of relaxing the phrase exactly. And the motivation is perhaps suggested by the subtitle here we'll talk about as well. So what this says about measures on homogeneous spaces arising from such representations. Okay. So with that motivation, let's start introducing some notation. In order to talk about, say, relaxing the phrase exactly, for instance, to the phrase approximately, it's best to consider a sequence of things. So I'm going to work with a subset, I'll call it capital H. A set of positive reals. We can take it to the accountable set if you like. And they'll be assumed to accumulate at 0. So for example, the inverses of the positive integers would be an acceptable set, or the interval 0, 1. So I'll denote by H an indexing parameter. And for each such, I'll assume given a unitary representation pi h of this Lie group G. And one more thing. Over here I use the symbol pi to denote a single representation. For the rest of the talk, pi will not denote a representation, but rather the Cartesian product of these representations. So a typical element in pi might be denoted as by the symbol v, and that'll correspond to a sequence of vectors vh. All right, so definition. So in order to say where we're going, we need to introduce a few definitions. So the first thing we'll do is we'll define an approximate version of equivariance. So we'll say that a sequence of operators acting on the various pi h's is, let's say, approximately equivariant if the following estimate holds for all non-negative integers. To define the estimate, I'll introduce a small extra bit of notation on this board that applies to a single representation. So we'll notice the definition of equivariance involves this difference between GA and A. So I'll define, perhaps up here, D subscript G A to be that difference from above divided by the distance from G to the origin, where distance is any reasonable distance function. Take a fixed norm of the Lie algebra, push it forward under the exponential map. That'll work for our purposes. Now the condition over here, we'll say that the supremum over H and H, the supremum over group elements, at most n of them, of the operator norm of several iterates of this map dg applied to the H element of our sequence of operators just be a finite number. So in other words, what we ask for is, I have a sheet introducing the action of the Lie algebra and the tensor algebra on that, but what this really says is we ask for uniform operator norm bounds of all derivatives of fixed degree. So that's the informal gist of this definition. So the importance of this definition for our purposes is just that it gives a characterization intrinsic to the representations of the only operators that we'll care about. And those will be described in the following example. The quantifier on L, you said? Oh, sorry. For all n in positive integers. Yeah. Thanks. So example 1, let's suppose correct. This could be any sequence, absolutely. Yeah. With the next definition, we will care. Yeah. So let's suppose that each pi h belongs to some space L2 of x for some nice right G space x. So you can take a smooth closed manifold, for example. Some space where integration by parts works. That's what will matter. And then just let f be any, say, fixed, continuous, compactly supported function. It would suffice to even have it just have all derivatives bounded. So we'll define some operators. I'll denote the operators by AFH. They ultimately act on pi h, and they'll be given basically by multiplication by f. And then to get an operator on pi, we have to project back down to pi h. So for example, if we unwind this definition, this says that the matrix coefficients of these operators on the vectors vh are given by the integrals over x of vh squared times f. Okay. This is another way of defining the operator. And then the assertion, which is a consequence of integration by parts, is just that this sequence of operators is indeed approximately equivariant. So we've imposed some fairly weak regularity condition on a sequence of operators, which we should think of as morally meaning they come from multiplication maps on some fixed space of some nice test functions. The important point is just that it's a notion intrinsic to the representation. It doesn't make any reference to the space. Okay. So for the next definition, we'll need the Lie algebra. And so what the following definition aims to capture is, we view Scher's lemma as a classification of equivariant operators. It's somehow too hopeless of a problem to classify equivariant operators in some very general sense on all vectors. So what we'll do is we'll single out some classes of vectors for which we can hope to say something more. Now in an irreducible representation, vectors kind of all look alike unless you break them down somehow. It's kind of already an atomic entity. So what we'll do is we'll take the representation, say pi h, and we'll decompose it by the action of group elements of size roughly big O of h. So that's what the following definition aims to capture. If we take a functional in the Lie algebra, we'll call it lambda. The definition will say the following. Say that a sequence of vectors, so v, which as always we'll denote by vh, in this Cartesian product pi is localized at lambda if for each compact subset, I'll call it theta, of the Lie algebra, the supremum over all elements of this set of, I'll write the notation pi, Okay, so now that I've finished writing the definition, let me read it. So we ask that if we look at any compact subset of the Lie algebra, that gives us some fixed notion of group elements, say x of hx, which are roughly within a distance h of the identity. Now what this says here is, if we pretend the right-hand side is 0, for example, the right-hand side is intended to be small. What this says is that the vector is roughly an eigenfunction under group elements set size big O of h. Now group elements of size big O of h, we're looking very, very close to the origin in the Lie group. So eigenvalues for such operators are naturally indexed by imaginary functionals on the Lie algebra. So that's what the definition is intended to capture. To elucidate it, we should probably give an example, because, for example, it's not clear that this definition is non-empty, or that maybe it's exhaustive, maybe it's too broad to be useful. So let's just introduce a small bit of notation that'll come in handy. So we'll write pi of lambda for the set of vectors that satisfy this definition. And we'll write lambda, capital lambda of pi for the set of lambda such that this space is non-empty. So lambda pi is some subset of the dual of the Lie algebra. We should ask ourselves, how big is it? What does it roughly look like in some examples? So I'll do the example of SO3, for which there's a basis of the Lie algebra given by the infinitesimal rotation matrices about the various axes that satisfy relations like this relation here. So there's so let's assume that each pi h is irreducible. And as a fact that, so what I'm going to say now is just the assertion that representations here are characterized by their Casimir eigenvalue. So the fact, which I'll state in the following form, is there exists some number I'll call ch, which will be h to the negative 2 times a non-negative integer, such that, so I'm going to let the Lie algebra act on pi h by differentiating the normal action. I'll denote the differentiated action by d pi h. And the assertion is then we can make sense of d pi h at sums and products of tensors and this will be exactly negative ch times the identity operator on pi h. This is the assertion that a representation has a Casimir eigenvalue. So if you stare at this condition on d pi h, and you at least formally reconcile it with this condition on vh, So you deduce, with a bit of argument, that lambda pi belongs to some bigger set, which I'll call script O pi. I'll define it to be the set of lambda, which satisfy the following quadratic equation. So the sum of their values on these elements here should be C, where C is defined to be the limit of the CHs in 0 infinity, and we assume that exists. So the conclusion is that we can draw a picture. So we have O pi. It looks like some sphere of radius C. And we have some obvious containment of lambda pi and O pi. And it turns out if you stare at any reasonable model of the representation, you can cook up enough vectors to show that in fact there's an identity here. So the set lambda pi in the example of SO3 is just some sphere. If the sphere is of infinite radius, it's defined to be the empty set. To give another quick example, for G is PSL2R, which we can think of as the connecting component of SO12. So a similar computation using the Casimir eigenvalue shows that lambda pi is at least contained in some set O pi, which will be the set of lambda that satisfies some degree 2, or signature 2-1 equation. Equals C, thanks. So there exists some C in maybe the extended reals. So we can again draw a picture of the set of lambda that satisfy this equation. Depending upon the sign of C, we'll get some different results. So if C is less than 0, we'll get a one-sheeted hyperboloid, some surface of revolution like that. If C is greater than 0, we'll get a two-sheeted hyperboloid. So it'll look something like, we'll have two halves, one down below, one above. And if C is equal to 0, we get some kind of degenerate case in between the two, where there's this one point here where it's kind of singular. And so, I mean, if you're familiar with the representation theory, yeah?
So what's the assumption on the representation of SO2R in this case?
An irreducible unitary representation. Yeah.
But pi is the product of the pH, right?
Yeah, pi is a sequence of pi h's. So each pi h should be an irreducible unitary representation.
And there's an arbitrary choice. I mean, any sequence is okay.
Yeah, so take a sequence and then pass to a subsequence for which this limit of rescaled Casimir parameters converges. And if no such limit exists, then these spaces will be empty. So this is kind of not a serious restriction. So if you want, this picture here corresponds to the principal series representations of SL2R. And for such examples, it can be very easily verified that lambda of pi is the entire space. These correspond to the discrete series representations. So we have two connected components here. Let's call this one O plus pi, and this one O minus pi. So then lambda of pi will equal either the positive component or the negative component, as the pi h are holomorphic or anti-holomorphic. And we assume that all of them are one or the other category, or else these spaces will all become empty.
But in this case, C is discrete, right?
So in this case, it's kind of, so for an individual pi h, you want to think of this as being like hz. So the actual space is continuous in the limit. Yeah. And so there's I mean, I'm not going to emphasize this today, but there's a so Kirillov orbit method, I should just at least mention in words, because it's kind of the inspiration for drawing pictures like this to talk about representations. All right, great. So we got some pictures of what this space lambda pi looks like. And now we're going to use these two definitions of localized and approximately equivariant to cook up a definition of localized irreducibility. So the definition we'll take we just say that pi is irreducible at some specific lambda in lambda of pi if for each, so in the earlier Scher's lemma, which we could think of as a kind of converse to, or as a definition of irreducibility, we took all equivariant operators. So here we'll take all approximately equivariant operators, and we'll ask that there exist scalars, we'll call them Ca lambda h, such that for all v and pi lambda, the following identity holds: ah vh minus Ca lambda h vh should equal little o of the norm of vh. Okay. So this is a definition, and so far we said nothing particularly beyond definitions. So now we'll make a remark that is again kind of trivial but important. So the remark is, if G is any group element, and lambda is anything we've written down, we can look at the space, what I'll call G pi lambda, which I'll define to be the set of sequences GVH, where VH is a sequence belonging to pi lambda. So it's a sequence that localizes at lambda, and we just translate every element by the same group element. So in this space, a very easy computation shows is equal to pi of another lambda, call it superscript g lambda, where this is by definition the functional that sends a tangent vector x to just the adjoint action of g inverse on x. So it's just the coadjoint action on lambda. This is a fairly easy calculation to check. Falls right from the definition. So one consequence of this is, in particular, G in the stabilizer of lambda we have the following identity: G pi lambda equal pi lambda. Okay. So we'll make use of this remark in just a second. But before we do that, let me state the one non-tautological theorem for today. And let me just, as a legal disclaimer, say that until all of this is published and stuff, take it as tentative, under review, and so on. So the theorem, which I'll call theorem 1, says suppose either G is I'll be honest about what's written down. So PSL2R or SU2, and pi is arbitrary, or G is the unitary group on n letters, and pi has what I'll call regular limit parameter. Just to write down that definition, since it takes 2 seconds. So the pi h will have some highest weights, lambda 1 h through lambda n h. And then we can define some limit parameters, say nu I to be the limit as h goes to 0 of h lambda I h. And then the assumption asserts that these are all distinct real numbers. Okay. So under these conditions, we can assert the following. So I said that lambda in capital lambda of pi is irreducible. So just as a matter of notation, let's write lambda superscript irreducible of pi to be the set of such lambda.
Are you in the limit in
Yeah.
weight, or is just the opposite?
It's just require, I mean, these will be some real numbers. We just require the real numbers to be distinct. Yeah. So the theorem then says that under these conditions, we have, so I'll refer to lambda of pi as the spectrum. This is actually not a bad term because suitably interpreted, it is a spectrum of an action. But this will be called the irreducible part of the spectrum. And the assertion is that under these cases, pretty much everything is irreducible. So if we just look at everything that's non-zero, that is irreducible. And I should say we have a proof scheme in place that needs to be fleshed out that will hopefully show in somewhat greater generality that this kind of irreducibility phenomenon is pervasive. So this is the one non-tautological theorem that I'll state today. And now what I want to do is I want to state some consequences of having a result like this in hand that apply to these cases where we have it, but also kind of show a fairly general implication. So now we're going to return to the case of example 1. So we'll suppose that each pi h is in some L2x as an example 1. So theorem 2 will be entirely tautological, I warn you, but let's write it down. So for any sequences of unit vectors, let's call them VH and VH prime. We'll consider two sequences. Localized at some irreducible parameter lambda. So we'll say that the the set of weak limits of the measures, let's say mu VH, which will be the L2 mass of VH squared, and mu VH prime so these sets coincide. And in fact, they coincide in a fairly strong sense. So they kind of coincide along any subsequence. So we can say that after passing to a subsequence of H, there exists some measure, let's call it mu lambda on X, such that for all VH, as in the last theorem, we have a convergence here. Okay. So I hope the statement is clear. It says if we look at vectors localized at an irreducible place, then there's a single measure we can get as a limit. So the proof is just exactly what the definitions have been rigged up to give. So to write up the proof, so let F be as in example 1. So we attach to it some AFHs. These were approximately equivariant by integration by parts. And by the assumption that lambda is irreducible, we get that mu VH of F, which is just the same as this matrix coefficient. This will equal some CAF lambda H plus little o1. That's the CA lambda that comes from the definition of irreducible, right here. And this quantity here doesn't depend upon V, so we can apply the same argument symmetrically to V prime instead of V. We get so that plus O1 and that completes the proof because we've tested this I guess equicontinuous family of measures on a dense set of functions. Okay. So already for SL2R, I believe this is a new observation that if you look at a sequence of vectors that are characterized by this very weak condition that I wrote down earlier, which I'll mention is pretty easy to check in practice, that they have to have the same measure limit. So the corollary of this that I'll state now is, well, I'll explain its context then after I state it. So theorem 3 says, so let's let mu lambda be as in the last theorem. So for any mu lambda as in theorem 2 and any element of the centralizer of lambda, we have this kind of property. So any of these measures are automatically centralizer invariant. So the proof is, so let's let VH be as in theorem 2. So the important remark that I stated earlier implies that the sequence GVH is also localized at lambda. And so then theorem 2 implies that g mu lambda, well, it's by definition equal to the limit of the GVHs. And this will equal mu lambda again. Okay.
Theorem 2 also will hold for the groups listed in Theorem 1?
No, so Theorem 2 and Theorem 3 are essentially tautological consequences of the definition. But this style of argument, I believe, is new. So recognizing that these definitions are actually useful to produce such an implication is perhaps the new part here. So for the groups listed in Theorem 1, so for example, for SL2R, so this generalizes something called the microlocal lift. So it was first given a complete proof by Zeldich, and then a different argument closer to our approach here by Walpert. So the comparison between this consequence and this classical result is this classical result applies to a constructed sequence of vectors with, they're kind of cooked up. There's kind of one sequence, and the proof splits into two parts, both that require some work. One kind of showing the positivity of the limit, the other showing the invariance. So the argument here differs in that, well, first it applies to fairly general vectors, much more general. And secondly, the invariance comes for free by this sort of argument. So in some sense, the proof complexity is cut in half. This is not the application I'd like to highlight the most, but just to put it in context, this is roughly where it stands relative to that construction. And so of course, if we look at these pictures we wrote down here, so the point relevant for the microlocal lift is if we look at the 0 axis and we pick, say, a point there. That's the case that corresponds there. If we stare at this picture, what this corollary tells us is that we'll get some SO2 invariance for sequences of localized holomorphic squares of holomorphic functions. In this case, it tells us that if we have a localized vector sequence of vectors in a sequence of representations where their eigenvalues grow sufficiently slowly, for example, if pi h is fixed, then we get some kind of unipotent invariance because the group stabilizing any point here will be unipotent. So this also, in this particular case for specifically constructed sequences of vectors, is known by Zeldich and perhaps other people. But the particular proof implication here is a new one and has some hope of applying fairly softly in some generality. And of course, for the unitary group and then variables, you never really get unipotent invariance out of this construction, and I'm not aware of any particular applications of this case, but it provided a good test for checking this in higher rank. Okay, so I'll use the remaining time to give kind of a high-level picture proof of this theorem. Theorem 1. So the description I'll give will either, for the better or the worse, it'll be a picture proof reconstructed from a more hands-on computational proof. So if it seems more well, I'll write it. Okay. So idea of proof. So remember, we have these spaces lambda of pi, or in these cases O of pi, basically the same spaces. And so I've reverse engineered this presentation to make the argument look like a microlocal analysis argument, which it would look like if we took the Heisenberg group in these examples. So that's the perspective here. So find a sequence of spaces, let's call them LH, that roughly converge to, let's say, lambda of pi as h tends to 0. So for example, in this example, you might take a sequence of spaces that look like hz times r mod z, which kind of converge to r times r mod z. You think of the circular wrapping around as the r mod z and the vertical axis as the hz. For the UN example, you do something similar with the spaces will be hz to the n choose 2 times r mod z to the n choose 2. And they'll come from Gelfand-Cetlin bases for these representations, if that means anything. And so then what we want to do is we want to basically pretend that our representation, or more precisely its tensor square, kind of roughly embeds inside L2 of these spaces. So we want to think of vectors in our representation, at least after we square them, as basically functions on these shapes that I've drawn up here. Such that, so I'm going to write WH for the image of some vector VH under this map. So this will be some function on LH. So now I'll write down some conditions that amount to saying that all the operators we look at, so for example, the group operators or these approximately equivariant operators, will act in this picture roughly like multiplication operators on this space. So if we take a tangent vector in our Lie algebra, so the rest of the talk is purely informal. Let me just say that. So when I say approximate, I mean something different. E to the hx vh, I'll ask that this inner product be approximately the integral of e to the I, I'll say LH of x, WH of LH, where LH of x is defined to be lambda h of x if LH corresponds to lambda h under this approximate identification. And also we'll ask that VH be approximately some integral of, all right, lowercase AH times WH over the space AH for some function AH. So the following proposition is purely formal, or informal perhaps. So if the sequence VH is localized at lambda, and the sequence AH is approximately equivariant, then WH is highly concentrated at, so I'll say the L that corresponds to lambda. And AH is a highly irregular function, I'll say. So I think it should have bounded derivatives and bounded values and so on. So a consequence of this proposition is that we can write this matrix coefficient AH VH. So this by our first assumption is roughly an integral of AH times WH. If you integrate a concentrated function against a regular function, it's kind of like integrating a delta mass against a continuous function. So you can replace this by just AH at the point where we're concentrated times the integral. And the assertion then is that this is independent of the sequence VH, whereas this quantity here is just the Ilp norm of VH. So if you're curious, the proof of this proposition formally follows by Fourier inversion using the fact that we're localized together with the first property written on the board up there. So that formally says you're a delta mass. Making that assertion sufficiently quantitative says you're concentrated. And by some more involved arguments, you can show you're regular here. And that at least formally gives the argument. OK, so I think I'll stop with that sketch of the proof. And, thank you.
Are there any questions?
So you said something about periods, to also be applied to periods?
Yeah, so the hope is to apply this argument and some other arguments to periods. So invariance is well known as an ingredient in bounding periods. And this is one engine that can produce invariance of limiting measures.
Can I ask a very silly question? Periods of what?
Oh, yeah. So I haven't particularly motivated the connection to this, but something like you have an automorphic function v on G mod gamma, and you integrate v over some subspace H mod gamma intersect H.
You integrate it with a flow cycle or something.
Yeah, something like that. We're integrating against a function downstairs. Producing invariance of the function upstairs, perhaps after thickening it a bit, is kind of a crucial ingredient in a lot of the techniques for bounding these things. So the emphasis is this is one particular technique showing this irreducibility in the sense we defined here of producing such invariance.
Is there any situation in which you can get rid of the going through a subsequence? I mean, take just the sequence and the conversions.
Yeah, so in fact, the argument here does not involve passing to a subsequence. Yeah, it's just to actually get a measure in the end. It's necessary to pass. Yeah.
Well, if there are no more questions or comments, we can maybe thank the speaker again.